Assalamualaikum warahmatullahi taala wabarakatuh, and thank you for our panel. My name is Adam Jawhari bin Jawahir. I would like to present my final project that has been supervised by Dr. Muhammad Irwan bin Adianto. My final project title is Seismic Design of Low-Rise Reinforced Concrete Residential Building in Peninsular Malaysia. This is my presentation outline. We start with introduction, problem statement, objective of study, scope of study, literature review, methodology, result and discussion, lastly conclusion. We'll start with introduction. For introduction, a quake is an event that we cannot anticipate. It can cause death, destroy buildings, tsunami, landslide, and a quake occur when two earth plates slip into each other, and it starts at the hypocenter of the earth. And this is the seismic hazard map of Peninsular Malaysia. Problem statement. First, residential is a place or building that should protect us from any danger. But there are many buildings affected during earthquake in Ranau, Sabah on June 2015. While residential building, it must sustain during any disaster like earthquake because it need to protect us from any danger. There are two objectives of study for my project. First, to determine the influence of magnitude of peak ground acceleration (PGA) on the amount of steel reinforcement. Second, to determine the influence of concrete grade on the amount of steel reinforcement. Scope of study for my project: 4-story RC building, which means hostel, assisted as the main model. 4 different magnitude of PGA equal to 0.04G and 0.06G for ductility class low, and 0.06G and 0.09G for ductility class medium will be considered for design. 3 different grades of concrete will be used for these research. It is G25, G30 and G35. Model will be designed based on Eurocode 8 2004 and Malaysian Annex 2017 for Peninsular Malaysia. Analysis and design will be using Tekla Structural Designer software. All model will be built on soil type D. The result has been discussed in terms of comparison of steel required as reinforcement, influenced by magnitude of PGA and concrete grade. My research has been supported by literature review that you can read in the slide. This is a flowchart of methodology for my project. Phase 1, generating basic model. Phase 2, structural modeling in Tekla Structural Designer. Phase 3, structural analysis and seismic design in Tekla Structural Designer. Phase 4, performing the taking off. Phase 5, cost estimation and comparison. Phase 1, generating basic model, which is low-rise building, 4-story hostel building with 3.35 meter height for every story and 504 meter square area for every floor. And the building is multi-story and multi-base RC frame. And this is list of model that has been used for my research. Phase 2, structural modeling in Tekla Structural Designer. This is the front view of RC hostel building and layout for ground floor level. For the building, we use two typical beam and two typical column, which is BA, BB, CA, CB. BA, the dimension is 200 mm by 500 mm. Beam B, 200 mm by 300 mm. For column A, 375 by 375 mm. Column B, 400 mm by 400 mm. As you can see, this is my load case in 4-story RC hostel building. Phase 3, structural analysis and seismic design using Tekla Structural Designer. As you can see, this is the step for run the design. First, click the seismic wizard to set up the parameter. To set up the parameter according to the situation. 3, click design button to design and analyze the building. Phase 4, performing the taking off. Taking off will be proceed only when all the design pass without single fail on the structure. Amount of steel reinforcement will be calculated from beam and column. Total amount of steel reinforcement will be calculated for 1 meter cube of concrete. Total amount of steel reinforcement will be compared according to the parameter. Phase 5, cost estimation and comparison. Calculate the cost estimation for entire building for each model and do the comparison. Then we proceed for the result and discussion. This is two graphs of design response spectrum. The first one is for ductility class low, then the second one for ductility class medium. The ductility class low with high level of seismicity is 0.0 G is considered to have higher design response spectrum. This is table for spectral acceleration of the fundamental period of vibration SDT1 and base shear force. As I tell before, all model has used same dimension for beam and column. As the result, the concrete volume for one building for every model is equal to 243 meter cube. This is a result for the total weight of steel reinforcement per 1 meter cube concrete normalized to non-seismic model for concrete grade 2025. These are the percentage difference of weight of steel reinforcement per 1 meter cube concrete normalized to non-seismic model for concrete grade 25. PGA 0.06 is 60%. PGA 0.06 G is 150%. PGA 0.07 G is 20%. And PGA 0.09 is 500%. Sorry, 50%. The highest percentage difference of weight of steel reinforcement per 1 meter cube concrete normalized to non-seismic model for concrete grade 25 is DCL, which means ductility class low with PGA 0.06 G. The value is 150%. This for concrete grade 30. PGA 0.04 is 50%. PGA 0.06 is 110%. PGA 0.07 G is 20%. And PGA 0.09 G is 40%, and the highest percentage is ductility class low with PGA of 0.06. The value is 110%. Then lastly, for concrete grade 35, PGA 0.04 is 50%, 0.06 is 140%, PGA 0.07 is 20%, PGA 0.09 is 40%. The higher percentage difference of weight of steel reinforcement per 1 meter cube concrete normalized to non-seismic model for concrete grade 35 is ductility class low with PGA 0.06G. The value is 140%. From the three result based on concrete grade 25, concrete grade 30 and 35, the higher percentage difference of weight of steel reinforcement per 1 meter cube concrete normalized to non-seismic model for concrete for grade concrete is grade concrete 25 with PGA 0.06G. The value is 150%. Next, we continue to total cost of material use. First, concrete grade 25 with price RM 300, 25 and 30 cent per meter cube. Concrete grade 30 RM 372 and 10 cent per meter cube. Concrete grade 35 RM 394 and 70 cent per meter cube. Height tensile bar RM 3 ringgit and 50 cent per kg. The highest total cost of material for one building is for concrete grade 30 with ductility class low, PGA value of 0.09G. The lowest total cost of material for one building is the non-seismic design. This is the percentage difference of total cost material for normalized to non-seismic model for concrete grade 25. 0.0G PGA is 30%, 0.06G is 70%, 77%, 0.07G is 13%, and 0.09G is 24%. The highest percentage difference is 0.0G with value 77%. This is for grade concrete 30. 0.0G is 21%, 0.06G 65%, 0.06G is 10%, 0.09G is 20%. The highest percentage difference is PGA 0.06G. The value is 65%. Lastly, concrete grade 35. 0.04G is 21%, 0.06G is 53%, 0.07G is 10%, 0.09G is 19%. The highest percentage difference is for PGA 0.06G with the value 53%. And next we continue with the conclusion. First, for the objective 1, to determine the influence of magnitude peak ground acceleration PGA on the amount of steel reinforcement, is total amount of reinforcement required in a building is higher when it designed to the higher magnitude of PGA and its on ductility class. The total weight of steel reinforcement increased around 25% to 150% higher compared to non-seismic design. The higher the magnitude of PGA in DCL, which is 0.06G, has the higher value of response spectrum, and it's the higher value of response spectrum as DT1 resulted in higher value of base shear force. The bending moment will be increased, resulting in higher moment of steel reinforcement required for the whole building. Objective 2, to determine the influence of concrete grade on the amount of steel reinforcement. First, the total amount of steel reinforcement required for RC residential building with seismic design when built with concrete grade 25 is higher compared to other model built with the other concrete grade. For PGA 0.06G, the total weight of steel reinforcement increased around 150%, 110%, and 140% higher for concrete grade G25, G30, and G35 respectively compared to non-seismic design. For future recommendation, the various of soil type should be considered in this study. Then second recommendation, extend the study using high-rise building as this study focus on the low-rise building. Third one, consider the other element like slab and foundation. That's all for my presentation. Thank you very much to our panel, and thank you.